Oh, hi. Welcome. Can you hear me? Bird is chirping outside. Hear me? It's chirping outside. Yeah, we'll start in 2 minutes. Two minutes. Oh, the sound is a little bit weird, huh? Like, can you hear me saying full sentences? Or just like a bunch of syllables at the end? Because I'm also watching my own stream on the phone. It's not. The sound is a little bit weird, huh? Like, can you hear me saying full sentences? Or just like a bunch of syllables at the end? Because I'm also watching my own stream on the phone. It's not. The sound is a little bit weird. All right. That's. Like, can you hear me saying full sentences? Or just like a bunch. All right, fellas. Then let's begin. So today's live stream, as you can see, is my first attempt at abstract algebra.
My own background in algebra is pretty weak. I only taken formal courses on linear algebra, a 2-semester worth of linear algebra, and they are like box standard linear algebra courses in universities. So I figured I would do this stream not just to show the math, but to give an honest process of how self-studying mathematics looks like, higher mathematics looks like, especially like proof-based mathematics. This is the perfect subject in my opinion, because you will barely see any calculation, if at all. The whole process is about understanding the definitions and finding the techniques, the main techniques for establishing a new theory. So for those who don't know, and I don't know very well, but just as an idea, rings and fields are algebraic structures. What do we mean by that? A ring is the generalization of integers, and fields are generalizations of rational numbers. So the idea is we don't really care that much of what the elements of an object called ring look like. So first of all, a ring, as I said, is an algebraic structure. What that means is it's a set equipped with some algebraic operations that satisfy certain rules, and those rules behave like how you would add and subtract, multiply integers. The details of the operations does not matter to us. The detail, we only care about the rules. We're not going to actually give an algorithm, so to say, of how to calculate multiplication between elements of rings. And the same is said about fields. But today we're only going to touch rings. Okay, we're not going to go into fields, most likely not. And that's the idea of the stream. Like, you're guaranteed to see a lot of me struggling, because that's okay. I think that's okay, because the whole point of this channel is about doing mathematics, is about inspiring each other to do mathematics. It's not about showing how smart I am. It's never the point. And it's not a PR department of mathematics. Right? It's often the case that many math content online aims to show the beauty of mathematics. Of course, math is beautiful, but it's, in my opinion, that beauty is not observed, it's experienced. And sometimes you gotta get your hands dirty to really appreciate the beauty. That kind of beauty that only can be felt after numerous failed attempts at certain concepts. Right? So there's that. It's like the view you got after climbing a mountain. You put in the work, your body is dying, but then you got this amazing view. Okay, that's the idea. And okay, so without further ado, let's just take a quick look of the main text we will be following. And these are all free resources, which I put in the Discord server. The primary resource is this one, is the notes for the course PMATH, meaning Pure Math 334, at the University of Waterloo, named Rings and Fields. This is a professor at Waterloo. And just to give an idea of what the level of this course is at. So here I have I think there's a course website here's a course the course description website, not the website of the course. Of course, that's unavailable. All right. So that's the, let me enlarge that, just to give an idea of what the level of the course is at. So this is the calendar for pure mathematics at University of Waterloo. The pure math courses all started with the number 300. So these are meant to be third year courses. Okay, so typically Calc 1 to 3 and even 4 are 100 to 200 level courses. Linear Algebra 1 and 2 are 100 and 200 level courses. So these are meant to be taken after you complete those sequences, even though there's no strict prerequisites when it comes to that. Of course, the strict prerequisites are given here, which I will give a brief description about. Okay, so here, as we can see, PMATH 334, Introduction to Rings and Fields with Applications, sits right here. And there are a few parallel abstract algebra courses. Young Galois is staring into my soul. Yeah. So, and speaking of which, there's a course alone on Galois theory. So Galois theory is very hard. And when Galois first put out his theory, not even the top tier mathematicians like Cauchy and Poisson could comprehend. And he died very young. So anyway, it was a very romantic story in the history of mathematics. And some part of it is actually exaggerated. But anyway, so this is where the course is sitting at. Okay, so it's meant to be like a first introduction to abstract algebra. Okay, and the prerequisites here says Math 335 or 235 or 245. What this means is this is linear algebra 2 in Waterloo system, and 245 is like the honor version of linear algebra 2. Okay, and another course that runs in parallel is Introduction to Group Theory with Application. So group theory and rings and field theory are separate courses. There's not a single Introduction to Abstract Algebra at the University of Waterloo. Okay, and you can see the prerequisites are the same, which means you can start with either. Okay, I also put the Waterloo resources on Pure Math 336 in the Discord. So if you're interested, you can check that one out as well. Okay, and here, so these are the more general courses. So this means if you are not a pure math major at the University of Waterloo, oh, by the way, this is if you're already taken Math 235, if you've already taken linear algebra 2, that means you already completed the introduction to proofwriting at the first year. So there's that. Right? You in order to do linear algebra 2, you first have to complete a introduction to proofwriting. So what it happens, so what it's like is that when we, I mean, I just gave away, I'm from Waterloo, but anyway, so in your first term, you take, in the first term, you take Calc 1, and not linear algebra, but rather a course on Introduction to Mathematical Reasoning that sets you up with the basics of the language of abstract mathematics, like logic, set, okay, equivalent classes, those sort of things, and you do some basic number theory in those courses as practice of those language, and that's your first half of your first year, okay, and in your second half of your first year you do linear algebra 1, right, and then in your second year you can do linear algebra 2. So that's the idea. So if you have finished Math 235, it means you already have some experience in proofwriting under your belt. But I know everyone's background is different. For example, if you've only taken a calculation-focused linear algebra class. A good complement for that as a prerequisite would be Introduction to Proof Writing, which I also provided a resource a few days ago on, let's call How to Prove It. Okay, because if you have no experience whatsoever in proof writing, this course is not very realistic for you. Hi, Vizzy. You're right. All right, so there's that. By the way, I was about to say that these two, Pure Maths 334 and Pure Maths 336, are meant for general audience. So if you're in the math department, you can take them, and if you have completed the prerequisite, right? That's the idea. That's the idea. And there's also more advanced version for pure math majors. I mean, even though the course is called Pure Math, but for pure math majors, they have their own separate courses. Okay, so that would be, you see, Pure Math 334, groups and rings. Even though the prerequisites are the same, this is usually what Pure Math major takes, because there's going to be certain courses that comes after this one, calling this one as the prerequisite and not 334. Okay, so if you want to go deeper into abstract algebra, this is what the department recommends. Even though the title is still group and ring, so the number is bigger, this tends to be more advanced. Okay, so this is what the actually this is group and rings, not rings and fields, right? So, so for the pure math fellows, as pure math majors, they would take Pure Math 347, groups and rings, as well as Pure Math 348, fields and Galois theory. Okay, I don't think the notes for 334, this one here, would get into Galois theory. It didn't say. Okay, so these two are more advanced, and the rest is not concerned. These are analysis and geometry and stuff. Okay, and yeah, and in the fourth year, there are some courses that depend on 347, right? As you can see. If you want to do fourth year pure math, you have to take 347. I couldn't quite find the material on 347. Okay, the only free resource is 334, which is okay for us. All right, so that's a brief background of what these courses are about. So just to have an expectation. And as Riggle Stats rightfully pointed out, these notes can sometimes be quite dense and terse. So I found another resource to help me out. It's like a dual text approach. It's something I use a lot of the time. I don't want to just get stuck with one resource and then make no progress there. So here's another resource, which in my opinion seems a little bit more gentle. Right. So this book is also free. I put it in the Discord. It's called Abstract Algebra, Theory and Application by Thomas W. Judson and Stephen F. Austin. Stephen, this is the name of the university, no? This is not the name of the author? Probably not. Okay. Anyway, so that's the book, and this is a more comprehensive introduction to abstract algebra, but I guess because due to the length, it's probably not as in-depth as the Waterloo notes, but that's okay. We just want some alternative resource just in case when we get stuck and have something to look up. Right. So as you can see, this notes start with something more fundamental. Right. So I guess it even has a short note on proof, sets and equivalence relation, just to brush up some of the basics. Right. The integer division algorithm. These are first year stuff. And it started from groups, which is fairly typical in many abstract algebra texts. And the rings only started at chapter 16. like almost over halfway. Okay, which, well, I think that would be okay. That would be okay. So we're just going to use this as a reference. Perhaps this will, I mean, I have no experience. I don't know this will be a good reference or not. But I guess something is better than nothing. I try to give free resources. I mean, I can refer to Dummett and Ford. That's like the encyclopedia of abstract algebra, very well known. But if no one can see it on stream, it's not going to be very helpful. Right? I have the book, but I can't show it on stream due to copyright stuff. Historical normal schools and tech stuffs. Okay, great. School for teachers. That's awesome. That's awesome. Yeah. So yeah, there's that. So that's an alternative resource, which we might look into. And it's also got exercises and references for suggested reading, so that's pretty great. And also has hints and answers to selected exercise, so that's helpful for us. All right. So let's get into the text. The first thing we should always do is to read through the preface. It's like an instruction manual, the README for a software. So there we go. So this is the preface to the second edition. Some typos fixed, all right. Preface to the first edition, let's look at that. The following is a set of class notes for the Pure Math 334 course I'm currently teaching at the University of Waterloo in January 2021. They're work in progress, and this being the first edition, they are replete with typos. All right, hopefully most of them are fixed in the second edition. A student should approach these notes with the same caution he or she will approach buzzsaws. They can be very useful, but you should be alert and thinking the whole time you have them in your hands. Enjoy. I think I would say the same about my own videos, actually. And a lot of people have already pointed out some of the typos in my videos. Thank you very much. And I think it is warranted for me to do second editions of my videos, right? Like rework videos. After all, mathematicians write second editions of their books all the time. Some of the most popular texts are like in their 12th edition now. So I think it's justified for me to rework my video and re-upload. So it's not, that shouldn't be considered cheating. That's my own justification. All right. Just one short comment about the exercises at the end of each chapter. These are of varying degrees of difficulty. Some are much easier than assignment questions, and some are of comparable level of difficulty. Those exercises that mark by 3 asterisks are definitely worth doing, as they are crucial for understanding the underlying concept. Okay, this is the first useful thing we've learned. I mean, the first paragraph is also useful. That's like a health warning. But anyway, this is actually important for reading. 3 asterisks. Exercises with 3 asterisks are definitely worth doing. Got it. Let me save that. All right. Anyway, as they're crucial for understanding the underlying concepts. The marked exercises are also of varying levels of difficulty. You mean the marked exercises without the 3 asterisks? Some other marking symbols? But it is better for the reader to discover some things on his or her own, since the reader will then understand and retain those things better. Besides, the only way to learn mathematics is do mathematics. Yeah. In our humble opinion, an excellent approach to reading these notes is as follows. Okay. This is exactly what I'm looking for. One first gathers the example of rings from the second and third chapters. Okay. So it looks like we have to do some nonlinear reading. We first need to gather a bunch of examples, and we will be writing our own notes, as always. One then reads the statement of the theorem, proposition, and corollaries. I see. I guess the idea is to first look through the examples and see why definitions are made, etc., and interpret those results for each of those examples, right? That's really nice, right? That's, I guess, I mean, this kind of goes without saying, but for someone who first entered the field of abstract mathematics in general, it's always a good idea to interpret the general results for specific examples. The interplay between abstract and concrete, theorizing and application, is what makes mathematics so interesting. Okay. Anyway, so this is like a mathematical maturity thing, and we'll take that as I mean, of course, we'll take that, but the important thing is the examples are from the second and third chapters. Now we know. Excellent. The purpose of the theory is to understand and unify the examples. Makes sense. Second bullet point. To learn the proofs, we recommend that one reads the statement of a given theorem or proposition and tries to prove the result oneself. Wow. Okay. We'll see about that. If one gets stuck at a certain point in the proof, one reads the proof until one gets past that point, and then one resumes the process of proving the result oneself. Okay, we'll try to do that. Also, one should keep in mind that if one does not know where to start, one can always start with a definition. Yeah, this is actually something I always say on the stream as well, right? So always go back to the definition, which means one always know where to start, just saying. All right, so there's another books that the author recommends, and gives thanks to the following people. Okay, I think we can skip those. Let's here's some interesting quote if you have time, but now let's just get into the actual math. Oh, by the way, the content list is also important. We were reminded that in chapter 2 and 3 we would find examples of rings. And indeed, chapter 2 is an introduction to rings. Chapter 3 is integral domains and fields. Okay? And especially important, I suppose, are the supplementary examples. Nice. And we also have exercises at the end of the chapter, which will be the star of the show. Chapter 1 is a brief overview. Okay, so how about we set our goal today to be chapter 1, and we will do some chapter 2. Okay, we're not gonna go into chapter 3 today. Okay, and I wrote in my post that one of the ways to read math book is to set a goal. I give in my post and the example of reading stochastic calculus. Right, so I was saying, if you want to understand stochastic calculus, you set a goal. For example, understanding the Black-Scholes formula, right? But that already assumes you have some rather surface level understanding, or not understanding, but just impression of what the subject is about, right? Like, for example, for abstract algebra, I can only name drop a few things. I know about Galois theory, but certainly that's out of reach. Put that as a goal would be unrealistic, right? So that's another difficult thing about self-learning mathematics. You don't know, I mean, you don't know a priori what would be a realistic goal, right? So that's kind of painful. And sometimes if you just set your goal to be, I want to understand this chapter, this can still feel rather aimless. That's why we encourage everyone to communicate, right? To communicate. So you can ask in the Discord or my YouTube community or comments, does anyone has experience with, say, a subject like abstract algebra? What would be a realistic goal in terms of actual results? So which theorem should I prioritize? Okay, so I think that would be an excellent discussion to to get the ball rolling when it comes to self-study. Right? We don't have to suffer in silence. All right, so how many chapters are there in total? Let's take a look. So these are, in total we got 10 chapters. And some of them are applications, I suppose. I mean applications in mathematics, not in the sense of applied mathematics. For example, chapter 10, we got the old famous problem, straight edge and compass construction, which I think is an application of field theory. Okay, do we have any applications of the ring theory? I don't know. It doesn't say. It doesn't say. Okay, so that's something I guess we need to bear in mind of. Let me put that on the note. Applications of, because applications always motivate. Right? Applications, I mean, it can be applied to the real world or an application in math itself. Anything that helps us understand stuff, right? Applications of ring theory, it's unclear from the notes. Okay, but that's okay. We'll keep that question in mind, or you can chat GPT it. I know, I mean, it doesn't say, right? It says, right? Chapter 10 is, it mentions field, right? It mentions field. So chapter 10 is an application of field theory. So this is something to look forward to. Anyway, there's an appendix on the axiom of choice, and that's about it. And we also have an index, which is great. This is the unsung hero of every mathematics book. This saves you tons of time. Anyway, let's get into chapter 1, a brief overview. Groups. Pure mathematics is, we would argue, the study of mathematical objects and structures, and of the relationships between these. We seek to understand and classify these structures. This is a very vague statement, of course. What kinds of objects and structures are we dealing with, and what do we mean by relationships? The objects and structures are many and varied. Vector spaces, continuous functions, integers, real and complex numbers, groups, rings, fields, algebras. Yeah, there's an object called algebra. It's not just the name of the subject. There's an actual mathematical definition of what an algebra is, actually, like things like Lie algebra. Algebras, topological spaces, and manifolds are just a very tiny sample of the cornucopia. Okay, English is not my first language. This is a very fancy word. I guess a collection of objects. Anyway, I don't think that's important. Of objects which come under the purview, I don't use this word very often either, of modern mathematics. Anyway, in dealing with various members of a single category, here we're not using category, that's the category theory, in the strict mathematical sense. For categories that are also a structure unto themselves, we often use functions or morphism to see how they are related. Okay, anyway, so this sentence might look a little bit difficult. Let me explain. I'll just give an example from linear algebra. In linear algebra, there are two main topics. One is vector spaces, and another one is linear maps. A linear map is a morphism. It is a structural preserving map between objects in the same category. So we're in the domain and codomain, V and W are both vector spaces. And a linear map is an example of morphism. It preserves the linearity structure. Right? So, for example, an injective function, and here that's the author's example. For example, an injective function. Right, so once again, this goes back to proof writing basic. You got to know what an injective function is. Injective function also means one-to-one. I understand not everyone in watching the stream might know these definitions, but injective also means one-to-one. It means if a function from A to B, so to say, has this property, is one-to-one if for all x1, x2 in A, x1 not equal to x2 implies f of x1 not equal f of x2. So that's the definition of one-to-one. It means if the inputs of a function are different, their corresponding outputs must be different. So that is to say, mapping f, okay, the function f preserves information. It does not collapse them. Okay, so distinct inputs correspond to distinct outputs. You know, you can always trace back things. That's the injective function. An injective function f from a non-empty set A onto a non-empty set B suggests that B must have at least as many elements as A. Okay, so that's the example in set theory. Right? If there exists an injective function from A to B, so it goes like something like this. So let's say you have A, the set 1, 2, and 3, and the set B here must have at least as many elements as A, because that's the pigeonhole principle, right? If B has fewer elements than A, then at least 2 elements in A must have the same function value, which contradicts the injective assumption. Right, so B must be something like this, say A, B, C, D, 1 to A, 2 to B, 3 to C. Okay, it does not have to be surjective, meaning all the elements in the codomain can be taken. It does not mean that. Okay, there can be, so to say, redundant elements in the codomain. But as we can see, an injective function preserves information. If we know a function f behaves this way, given any element in the range of f, we know always what's the corresponding input. Right. In fact, you can construct an inverse function given an injective function. You can construct an inverse function. That is to say, if we restrict the inverse function f inverse to have domain ABC and codomain 1 to 3, you can easily write down the inverse function. F inverse maps A to 1, maps B to 2, and C to 3. Right. So an injective function implies that the codomain B must have at least as many elements as in A. Right? Yeah. Hi, Vizzy. I know you're watching, but yeah, thanks for following. Okay, so this is a rather generic description. Let's keep going. 2 principal structures we shall examine in this course are rings and fields. The typical approach in most books begin with the definition of a ring. Yeah. For example, and then produces a hopefully long list of examples of rings to demonstrate their importance. Yeah, as you can probably imagine, this is typically how mathematics writing goes. Okay, it gives you the definition at the start and then produce a long list of examples. Hopefully, this is mostly for economic reason. Okay, we give the overarching definition first and then give the example. And sometimes I do that in my own videos. So far, notice you are reading sentence and trying to draw figures to understand what the sentence is saying. Yeah, exactly. Yeah, exactly. Because I mean, I don't have prior experience with the subject, right? So I don't have a particular strategy of how to follow these notes. So I kind of have to give a linear reading first. But we will keep coming back to things that are said before, as usual. Okay, anyway. The process is, however, essential is essentially the inverse of how such a concept develops in the first place, indeed. In practice, one normally starts with a long list of examples of objects, each of which has its own intrinsic value. Through inspiration and hard work, one may discover certain commonalities between those objects, and one may observe that any other object which shares that commonality will, by necessity, behave in a certain way as suggested by the initial objects of interest. This is a process of mathematical abstraction. Right? The advantage of doing this is that if one can prove that certain behavior is a result of the commonality, as opposed of being specific to one of the examples, then one may deduce that such behavior will also apply to all objects in this collection and beyond. But enough with generalities. Let us illustrate our point through an example. Since both rings and fields exhibit a group structure under addition, let's momentarily digress to examine these. Okay, so far everything seems pretty easy to follow. Examples. Okay, and I think here it's time for us to be prepared to write our own notes, because we will be collecting those examples like jewelries, because these are crucial for us to contextualize theorems, because without those examples, it's very hard for your brain to get a hold on to what the theorem is saying. 1.3 example. Consider the following list of structures. A, the set Z of integers, which includes both positive and negative integers as well as 0. Note that Z admits a binary operation called addition. This is kindergarten stuff, which is denoted by plus. To say that addition is a binary operation on Z means that plus is actually a function on the set of ordered pairs of integers, Z times Z. Right? This is the set of ordered pairs of integers. Okay, this is the Cartesian product notation for ordered pairs. And sometimes we can write Z squared as an abbreviation of Z times Z. This is also okay. With range included in Z. That is, addition is a function that maps an ordered pair of integers to another integer. Notice how this says nothing about how integers is actually how addition is actually performed. So it's like a function template when you do programming. I mean, programmers out there in the chat, correct me if I'm not using the correct terminology, right? So you're just specifying characteristics of the input and output without going into the details of how do you actually implement addition. Right, so that's the first example. Second example, consider the next set, big N, of natural numbers, 1, 2, 3, and so on. Again, addition, also denoted by plus, is a binary operation on big N. That is, we have a function plus big N times big N to big N, ordered pair AB maps to A plus B. Okay, and just a short notational thing. You notice the difference between these two arrows, no? Yeah. So if you're indicating a map or a function that maps one set into another, we don't write the little vertical bar here. But if we're talking about the image of a specific element from the domain, we use the vertical bar notation. So it would be a mistake, strictly speaking, to have say you have Z times Z maps to this letter here is so this symbol here is called maps to. If you LaTeX it, it will be quite literally backslash maps to Z. This would be a mistake. Okay, this is not standard terminology or notation. Or if we write AB arrow A plus B, that's also incorrect notation. I know sometimes in physics we write this sort of stuff all the time, but that's not. I should have remembered that. Thank you. I want to study. This is how to study mathematics. I want to study the correct way. Controversial question. Do you write in a physical textbook? I used to, but I stopped doing so. Okay. Yeah, I stopped doing so because I think it's better to have my own notes. Yeah. If I have to put a mark on my book, I use pencil. I used to not be very careful and kind of made my books a mess, which I regret. Okay, because now I'm more of a collector of books now, so I care about their values more. Okay. Yeah, Vizzy, this is how to study mathematics. If I may say so, this is the way. Okay, what I'm doing is the correct way. Okay, I know it sounds extremely arrogant, but I mean, you don't have to take my word for it. You can, I don't know, perhaps show my, you can, I guess, if you have access, I mean, you're entering college or university, right? You can show my stream to a professor of yours and ask for his comment. Perhaps, and let me know about his feedbacks too. Right? So that's, yeah, just that's to answer your question. This is how I study, and it certainly helped me a lot in my journey. I've been self-studying mathematics consistently, both in and outside of university. I had a prof that used to say there are many ways to love a cat. Yeah, I suppose, because, I mean, I suppose this is not how Galois studied mathematics, or Ramanujan for that matter. This is how I do it. Right? I used to have an old video on my old channel that says the idea of studying mathematics is like being a detective. Right? Anyway, let's keep going. So, so far A and B should be quite straightforward. Right? These are just examples of a set equipped with a binary operation. And a binary operation is what? A binary operation is a map that takes an ordered pair of the original objects and turn into the new object into the original set. Right? That's a binary operation. C. Let n be in big N. So n is a natural number. And consider next to the set of n times n, n by n, complex matrices, okay, M and C. Given A, so these are square matrices. This is a set of square matrices. Given A equals Aij, so this is meant to denote the elements in A, Aij, and B equals Bij, because these are two matrices in the set M and C, and we can define the sum of A and B to be A plus B equals the element-wise addition. And this is completely usual operation. Right? Once again, this is a binary operation. You take two matrices of the same size and returns a new matrix of the same character. Right? So therefore, M and C is closed under addition. We say closed under addition. By that we mean the result of the addition is in the original set. The result of the addition is in the original set. Let me just give a counterexample to indicate what set is not closed under addition. The set of irrational numbers, is not closed under addition, because you can have examples like the square root of 2 plus 1 minus the square root of 2 equals 1. So the sum of two irrational is irrational. So irrational numbers are not closed under addition. Okay, anyway, part D. Part D, here we have some rather complicated notation. Scripted C, interval 0 to 1, and R. What does this mean? This means the set of continuous functions. The set of real valued continuous functions on the closed interval 0 to 1. Because sometimes the codomain R is obvious, so we just write C01. That's also quite common. Okay, the set of continuous functions. Given f and g in C01R, we may define their sum f plus g via the obvious definition. You just add up the function values, right, to get a new function. The new function f plus g evaluated at x is the sum of the values of f and g at the same point x. Right? So that's the sum of two functions. From first year calculus, we know that since f and g are each continuous on 0 to 1, so is f plus g. Right? Indeed, this is the standard result from calculus. The sum of continuous functions is also continuous. Once again, we say that C01R is closed under addition. Make sense? Q, this is the notation for rational numbers. Of course, rational numbers are defined as the ratio between integers. Right? So the rational numbers have the form P over Q, where P and Q are integers and the denominator is non-zero. Right? Denote the set of rational numbers and set Q star. So Q star is Q minus, this is this notation for set minus. You're removing elements from Q. Right? We're just removing 0 here. All right? So this is Q star, the non-zero rationals. And we're given R1, R2 in Q star. And let's write R1 as P1 over Q1 and R2 be P1. I think this is P2 over Q2, no? Yeah, that's a typo. This is obvious. R2 is P2 over Q2. Let's put that right here. P2 over Q2. And the product, R1 times R2, be P1, P2 over Q1, Q2 in Q star. Thus, Q star is closed under multiplication. All right, a little spelling mistake, but that's okay. If I'm only as observant when it comes to spotting mistakes or typos in my own videos. Anyway, we're always very sharp and fast when we spot other people's mistakes. Okay, I mean, that's just me. Okay, maybe you guys are more self-aware. I'm not. If we set Q plus, if we set, he hated cat, there are many paths to solution. All right, anyway, if we set Q plus, that's a positive rational, to be the set R in Q, such that R is positive, then Q plus is again closed under multiplication. Okay, so what is the point here, right? So we have all these examples, and which I think for most of you, this will have no problem following those, okay? So these are a bunch of facts. These are a bunch of facts. What's the moral of the story? What's the punchline here? The examples A, C, D, E, F. Why not B? B is conspicuously missing. All right, let's just play along. A, C, D, E, F have at least the following two things in common. All right. 1. In each case, there is a neutral element. Okay. Yeah, there's a neutral element. That is the element z in the set which satisfies a plus z equals a equals z plus a for all a in the original set. I see. So from all these examples, we all have the operation called addition. See? But now, right now, we're not looking at part B. We're not looking at the natural numbers with addition, okay? But everything else, I guess. Oh, so for Q, we're dealing with multiplications, the neutral element. The neutral element would be 1. Hang on, let me let my cat inside. That's why B is not in the list. Exactly. No inverses, no neutral elements as well. Yeah. So because to define inverses, you need the neutral element first. Anyway, I'll be back. All right. All right. So which kind of worries me because we're already using the plus notation for all these examples, but for E and F we're defining multiplications. No, there's no addition here because as far as E and F is concerned, we're not talking about addition at all. Okay, so this is kind of sus, but I guess I know what the author meant, right? So for example, where addition is defined, except B, you have a neutral element, right? For example, the neutral element in part A is just 0. The neutral element in part C is a 0 matrix. And the neutral element in part D is a 0 function, the constant function that takes 0 everywhere. All right, so that's it. Okay, let's continue. For example, in the case of Z, we simply set Z equals 0. Whereas for M and C, we need to set Z equals the 0 matrix. In the case of the continuous functions, we would set Z to be the 0 function. Right, so the 0 elements are simple, usually readily attainable from the context. And we don't usually distinguish, say, a 0 matrix and a 0 function with different notations. Right? These are obvious from the context. The meaning of 0 should be obvious from the context. In the case of Q star and Q plus, the number 1 serves as a neutral element under multiplication. Right? Indeed. Note that n does not possess a neutral element, regardless of which z is in big N, one choose n plus z does not equal n for any n. So I guess we are choosing a convention here. The set of natural numbers, as far as this set of nodes is concerned, starts from 1, not 0. Right? And that's the convention used in most analysis texts. Right? In, for example, real analysis, we also consider the natural numbers to start from 1. Right? I know in some computer science and logic courses, the natural numbers start from 0. Perhaps that's their convention. And I think in Python, if you define an array, the first index is 0. That always got me. Okay, I'm not, even to this day, not super used to that. But if, let's say, if you program in R or MATLAB, an array or a vector, in you program an array or a vector in R or MATLAB, the indices start from 1. I guess that's natural for most mathematicians. Anyway, so n has no neutral. If n starts from 0, it would have a neutral element. But for this set of nodes, we take the convention that n starts from 1. Second, Note also that for each element A in each of the first, third, and fourth example, hang on, first, third, and fourth example, you mean A, C, and D? Yes, A, C, and D. In A, integers, C, matrices, and functions. All right. So in those examples, there is such a thing called an additive inverse. There is an element B such that A plus B equals Z, which is the neutral element from 1, right, equals B plus A. This coincides with what we normally refer to as a negative or additive inverse of A. Right. For example, if you take the set of continuous functions, you simply just set minus f to be defined as the function that takes the value of f of x, but with an opposite sign, right? So that's the obvious definition for the negative f. Again, that negative f is continuous when f is continuous is proven in first year calculus. All right, so far so good. Given r equals p over q in q star, in using this notation, we're assuming that pq in z, okay, and q is non-zero, I suppose. We know that p is non-zero and q is not, actually, yeah, it's already assumed. It's already assumed that q star only contains non-zero rationals. We note that p is non-zero and q is non-zero. So q over p, yeah, q over p, we define s to be q over p is in q star. So s times r is 1 and r times s. So this means in q star you always have a multiplicative inverse. Right. We're excluding 0 to ensure that every element in q star has a multiplicative inverse. Once again, n fails this property. Indeed. Okay, so perhaps we should do a little bit summary here. We don't have to write down every word verbatim in our notes. I just do a quick summary of example 1.3 because this is a very straightforward example. Right. Example 1.3 examples should be examples summary. A is Z with the usual addition. So we can write something like this, by the way. It's not in the text, but this is standard notation. This means the set Z equipped with the usual addition. Okay. B. Hang on, why is not doing the labeling thing for me? Okay, hang on, this is, put the title notes on rings and fields. Today is June the 6th. What's the process of retaining information learned that you're doing? What is a retaining information? You will solve some problem, assume if this book contains problems. Yeah, it contains problems. And you know what? Shall we look at the problems? Are you guys getting bored with these examples? Yeah, you know what? Let's look at examples too. To look at the exercises to perhaps keep us motivated. All right, I'll just put the summary down real quick. All right, C is matrices. Yeah. Okay, so we've seen some examples of binary operations, right? Addition and multiplication, which is good. All right, let's see. Can we do some exercise? Probably not a whole lot, right? Probably not a whole lot. So, but it's good to have an idea of what is ahead. I guess the important part so far is getting used to the lingua, right? The notations and terminologies and stuff. Right? So these are some of the most common sets that we'll encounter in abstract algebra. You have the Q and the Q star. I'm not sure if the notation Q star is standard, no? I don't know. The set of non-zero rationals, is that a standard notation? Like to see how you use the information learned to solve a problem. Yeah, that's the idea. That's the idea. Without solving a problem, these things will be quickly forgotten, for sure. Exercises are the star of the show. All right, so that's the, it has the, I would say, yeah, so except for B, every example has a neutral element and an inverse. So let's put that down. Except for B. Oh, by the way, I forgot to put the multiplication. Okay, once again, C is equipped with addition. We're not discussing multiplication between continuous functions yet. Okay, and for E and F, for E, okay, Q star, just in case we forgot the definition, is defined as Q minus 0. Because I don't think this is standard notation, but we will take that in this book. Right, so this is Q star, and we are considering the set Q star equipped with multiplication. Right, and Q star plus is also equipped with multiplication. Q star plus, by the way, this is also worth writing down the definition, because sometimes in some books you write 1 plus to indicate non-negatives. Here we mean positives. Okay, some books, especially in economics textbook. All right, so agreed, I'm not bored. I had forgotten the script C for continuous functions. This is great for getting the rust off. Exactly. Sometimes the first chapter is great for just to get used to the notations. Right. So anyway, so Q star, Q plus. This means the set of positive rational, not non-negatives, because in many economics textbooks we often deal with the set of positive reals or set of non-negative reals, because quantities in economics like prices and goods cannot be negative most of the time. So economists use 1 plus to indicate, many economists use 1 plus sign to indicate non-negatives and 2 plus signs to indicate strictly positive. But here Q plus means rationals that are strictly positive. All right, so R in big Q are greater than 0. Right, once again, we're considering the operation multiplication. So that's the part F. So examples A, C, D, E, F all have a neutral element Okay, let's put the definition down. Definition, neutral element Z. Z. It's A plus Z equals A, which equals Z plus A. And that's true for all A. Or, in the context of multiplication, you would have A, Z equals A equals ZA for all A. For all A, all right? Okay, so that's the neutral element. That's an important observation, which we will come back to. And part 2 is that it also, except for the natural numbers, everything has an inverse or a negative. inverse. And also, they all have an inverse element. Okay, inverse element would work something like this. The inverse element for it also they all have an inverse element for. Actually, this is not good phrasing. Also, in each of those examples, every element has its inverse element, has a corresponding inverse element, right? That's good phrasing. So we write there exists there exists B such that A plus B equals Z, which equals B plus A. Sorry, and this is true for all A. Right, so that's the inverse element. Of course, we're using the addition notation, but this, of course, you can change that to multiplication for the multiplication examples, and that's depending on which operation you're looking for and where Z is the neutral element of the set. All right, so it seems to me like a okay summary. So now we can move on. Here you have more examples, but you know what? That's the act of writing out the note. You know, is a big part of the information retention. Exactly. I second that 100%. So, and always stand by what you write. Stand by what you write. And when we write our own notes, a good way to keep us motivated is to imagine a reader who has similar mathematical background as you, but may not know what you're writing. Okay, always to imagine that reader in your mind. Sometimes it will have an actual reader, and most likely that reader is you, your future self. Right. So be gentle on your reader. Anyway, so let's take a look at the exercise. I don't expect it to be able to do tons of exercise, but anyway, just to give an idea, exercise 1.1. This is a group. Okay, we haven't seen a definition of group yet, so we'll work on that. This is a group. Prove that if EF is in G is in the group, and GF equals GE equals G equals EG equals FG, for all G in big G, then E equals F. That is, prove the identity element of the group is unique. Okay? I guess we'll have to check the definition of group to come back to that. Okay, what about the rest of the examples? What about the rest of the exercise? Second exercise, also about groups. Third one, also about groups. 1.4. This is a specific group. We don't know the meaning of this yet, but we'll look into that. All right. And okay, so, we don't know what exercise 1.5 means either. Okay, so I think we can get back to the main text. Okay, just to keep in mind that most of the exercises are about groups in chapter 1. Okay, so hopefully by the end of the stream we can get to the definition of a ring. Hopefully. Okay, but let's not push ourselves. Okay, if there's a certain point at words pondering, it's better not to rush over them. Okay, so I think we can move on to example 1.4, huh? 1.4, example. The next example appears, at least on the surface, rather different from those above. Let, I guess, triangle denote an equilateral triangle with vertices labeled as 1, 2, 3. Okay? Let's think of triangle as sitting in the xy plane, sitting inside the 3D real vector space, R3. Okay? So let's draw a picture. That's the 3D space, R3, the usual 3 space. And the xy plane is here, and the triangle sits here. That's the mental image here. We equip R3 with its usual Euclidean distance or metric as follows. This is high school geometry, high school analytic geometry. If x equals x1, x2, x3, and y equals y1, y2, y3, and r3, the distance between x and y is defined as such. The Pythagorean distance, the Euclidean distance by the Pythagorean theorem. Right? So nothing unusual here. We first consider isometries of the triangle. By an isometry, we mean a map. Hang on, is that a set? This is a notation of a function, no? It's a map. It says phi from the triangle to R3. I thought this is a triangle. What are the elements in the triangle? Are the elements the vertices or points on the edges too, or inside? It's unclear. Okay. I guess we'll have to clarify that ourselves based on our reading. What do you guys think? Okay. In my opinion, this is rather sloppy writing. This is a triangle. Is that a set? Does it include the boundary? Nobody knows. Okay. The location of the vertices is how I interpret. So, wriggle step. You mean delta is the collection of 3 points. So let's just call right. So you got 3 coordinates, right? So that's what you mean. I'm not writing everything down, but is that what you're saying? So delta only has 3 elements. Anyway, let's keep writing. Let's keep reading. This is, yeah, that's how. Okay. Okay, but we will be we'll clarify that in our own notes. We mean a map phi from delta to R3 such that d of x and y is d of phi of x and phi of y. That is, phi preserves distance. All right. We then define a symmetry of the triangle to be an isometry of the triangle with the property that. Right, so this is the notation for image. By the way, this is the notation for image. Let f image of a function. Let f from a to b be a function. Okay, let f from a to b be a function. We write f of a as the set b in big B such that b equals f of little a for some a in big A. This is a notation for image with the property that A symmetry says, basically it says the image of the triangle is the triangle itself. That's a symmetry. That's a technical definition of symmetry. That's a technical definition of symmetry. So denotes an equilateral whose vertices is labeled as 1, 2, and 3. Perhaps an equally valid interpretation would be the points inside the triangle, including the boundary. And that's also, I think that's also valid interpretation, no? So imagine you have a triangle, which we interpret as the set of points inside and on the boundary. Right. Think about you're manipulating this triangle in some 3D graphics engine. You can lift it up, rotate it in space, but one thing you cannot do is to distort the image. You cannot stretch it, okay? You cannot scale it, okay? It has to be in the same shape and the same size. Whatever you do with this object, it has to retain the same shape and same size. And that transformation is an isometry. It's like a rigid motion. Okay, so there's that. And of course, because this is a triangle, all the points that are on the side and inside the triangle is determined by the location of the vertices. It's fully characterized by the location of the vertices. So I guess it's equivalent. It's equivalent of treating the triangle symbol as the collection of the coordinates of the vertices or the collection of points inside and on the triangle. I think the two descriptions are equivalent. But still, that would be, yeah, more verbose. That would be true though, right? Yeah, that's true. All right. So that's a minor inconvenience, but I think we can move on from that. So the symmetry says we might rotate the triangle clockwise through 0 radians, 2/3 pi radians, and through 4/3 pi radians about this center. Here's the center. In degrees, 2/3 pi radian would be 120 degree. And this is 240 degree. Indeed, if you rotate, because due to the geometry of the equilateral triangle, this is 120 degree. If you rotate that, if you do this rotation clockwise, like this way, right? So this is row 1. And if we apply row 2, that would mean rotating 240 degrees, like this way. So yeah, so 1 becomes here. Yeah, 1 gets here, 2 gets there, and 3 gets here. Do the rotation in your mind. Okay, so that's clockwise rotation. So this operation is a symmetry. So that's a symmetry because the image is the same. If we rotate by 180 degree, that would not be asymmetry, right? Because if we rotate by 180 degree clockwise, the triangle will be upside down. 1 gets here, 2 gets here, 3 gets here. This is not a symmetry. So that's a non-example. Oh, it's not allowed to be pulled up or down in R2. It's hard fixed in the XY plane. Oh, right. It's just in R2. Rigid motion in R2. Planar motion. Yeah, you're right. So this extra coordinate is useless. Okay, anyway, it doesn't matter. Yeah. Okay, so that's a geometric example. The action of row 2. Nice. We might also fix one of the vertices, for example, the top vertex, labeled 1 in figure 1. Okay, I don't usually keep my notes like this. I don't save these changes when I'm done. Okay, but I'm just doing it for the sake of the stream. So here we might also fix one of the vertices, for example, the top vertex labeled as 1 in figure 1, and reflect the triangle along the vertical line from the top vertex to the midpoint of the horizontal line segment. Yeah. You reflect the triangle along this vertical line, connecting the leftmost vertex to the right. Let me reread the sentence. For example, the top vertex, and reflect the triangle along the vertical line from the top vertex to the midpoint of the horizontal line segment, connecting the leftmost vertex, label 3, and the rightmost vertex, label 2, in figure 1. Right? Figure 1 here. Yeah, it's the same picture here. Nice. Let's call this symmetry phi 1. So that's a reflection. The 2 gets here, 3 gets here. That's a reflection. It's also a symmetry. The image of the transformation is the same as the input. Okay, let's call this symmetry phi 1. And symmetry is similarly obtained by fixing fixing vertex 2 by phi 2. Okay, what would phi 2 be like? Phi 2 would be reflection along this line. It fixes phi 2. Well, that's similarly obtained by fixing vertex 3 by phi 3. So phi 3 would look like this. Reflection along this line. Right. So far, we discovered 6 distinct symmetries of the triangle. Are there others? Right. This is interesting. So that's the question, right? So that's the question. A moment of thought will hopefully convince the reader that any symmetry must take distinct values, distinct vertices of the triangle to distinct vertices. Taking distinct vertices to distinct vertices is injectivity. That's injectivity. Right, so I guess following Riddlestat, we can just define delta to be the set 1, 2, 3. Right, so, and now let's consider functions on this set. To be a symmetry, it has to be it has to be injective. Right? To be a symmetry, it has to be injective, because if it's not, then what happened? Well, you got 2 vertices that got glued together. No, that's not the shape of a triangle. So yeah, there are only 6 ways of doing this. Okay. Once we've chosen where to send vertex 1, there remain 2 choices for where to send vertex 2. Yeah? Right? Yeah, if we decide where to send vertex 1, remember, to be a symmetry, the input and output should both look this way. It's just that the vertices can be labeled in different manner. So that's the original. Okay? And the end shape should be the same shape, same orientation. It looks exactly the same like triangle, like same position, okay, same orientation. Everything is the same, but only the labels can be different. And if you decide where to send the new label for 1, right, then you only got 2 choices for where to send to, and vertex 3 is completely determined. Right, so this becomes a combinatorics problem, so you should have 6 choices. Right, so that's the reasoning, and we just found those 6 choices, so we have them all. So that's pretty cool. Right, so this is a finite set, right? So, and we denote sim delta or sim triangle to be the set row 0, row 1, row 2, phi 1, phi 2, phi 3 of all symmetries of the equilateral triangle. And this will be an example of group, I believe. And this is an example of symmetry group, I believe. Okay, but I guess so far we're not dealing with, I mean, general definitions yet. But the idea is this is a collection of transformations. This is a collection of transformations that keeps the original shape and orientation intact. Okay, that's a technical definition of symmetry. I think we should write this down. What's the definition of symmetry? Symmetry of an equilateral triangle. Okay, let's put our notes down. Okay, so denote delta or triangle. The set of vertices, the set of vertices, 1, 2, and 3, of an equilateral triangle. Fixed on the plane. Okay. A symmetry triangle. What? A symmetry of the triangle. Symmetry of the triangle is an isometry. Okay. Let's just say this is distance preserving. I don't think it's necessary to write down the definition of Euclidean distance. We all know how that works. Dummy labels are allowed to be arbitrarily relabeled. What do you mean by dummy labels? So distance preserving maps. Okay, an isometry. A symmetry is an isometry with the property is an isometry. Let's just give it a symbol phi. With the property that phi of the triangle equals the triangle. Okay. So the collection of all symmetries we have the notation sim triangle. The collection of all symmetries of triangle has 6 elements. And this is how it works. One has 3 possible images. to send. After sending 1, 2 has few remaining possibilities. After sending 1 and 2, 3 has no option. Okay, so therefore you got 6 equals 3 times 2 times 1. Right, so that's the collection of all symmetries. And in particular, we can enumerate them. So we can, in fact, enumerate the set sim triangle. So sim triangle equals, I just write the normal row, I guess. Row 0, row 1. Row 0 is the identity. Row 0 literally does nothing. It rotates through 0 radian. Okay. Row 2, phi 1, phi 2, phi 3. Okay. Where row I, that row I is the rotation, is the clockwise rotation about the center by, let's use degrees, 120 I degrees. Okay, so that's the clockwise rotation. I equals 1, 2, and 3. Oh, sorry, not 1, 2, 1, 2, and 0, 1, and 2. And phi I is the reflection that fixes vertex I. The vertex I. Okay, so that seems like a decent summary. Right, so this is all the symmetries of the equilateral triangle. How about that? Question. The 1, 2, and 3 are labels. If 1 goes to 2, 2 goes to 3, and 3 goes to 1, you can just relabel them. We're not going to relabel them. Okay, we're going to keep track of how the transformation is done. Okay, we know the shape will be the same because we're only interested in symmetries. Right? So we're only interested in symmetries, so we're not going to relabel them. Okay, so let's say 1, 2, 3 in the original configuration becomes this way. We're not going to relabel them. We want to keep track of how the vertices got changed. Make sense? Even though the shape remains, the shape and the orientation remains completely identical. Right? We're not going to relabel those. We want to keep track of how things are transformed. Here, this is where it gets interesting. Suppose we choose to compose two of those symmetries. That is, we first perform one symmetry and then another. For example, we might choose to do row 2, first do row 2 and then phi 1. What would the result look like? You see, here we're using the same notation because the same notation as we did earlier. So we're transforming the labels, not the coordinates, just to keep things simple. So here, let's see. note that row 2 sends vertex 1 to vertex 3. Let's draw the picture here. This is 1, 2, 3 in this order. So applying row 2 gives us what? 1 is here, 2 is here, 3 is here. Right? So let's keep the information in a table. So row does what row does to each vertex. So 1 becomes 2. Hang on. Row 2 sends 1 to 3. Oh, right. So it says row 2 sends, this is row 2. Row 2 sends 1 to 3. Yeah, 1 gets sent to the original position of 3. This is how we keep track of information. 1 gets sent to here, and here is the original position of 3, and that's how we record the information. Sure, let's follow that. 1 to 3, and 2 to what? 2, well, 2 becomes, this 2 gets sent here, and that's the original position of 1, so it should be 2 to, row 2 should send 2 to 1, no? Yeah, indeed. And 3 to what? 3 can only go to 2. Yeah, 3 gets sent here. This is the original position of 2. Right. So this kind of like a permutation, right? This is a permutation. We can equivalently call this transformation a permutation. You just shuffle the orders of the original set. Okay, this is row 2. Similarly, phi 1, yeah, phi 1, we know phi 1, what's the picture of phi 1? 1, 2, and 3. Reflect so that 1 is fixed. This is phi 1. Right, and it becomes, by the way, did we start with the section groups? Okay, I forgot. A brief overview. This is a brief overview. Groups. Oh, we're still in the section groups. Right, still in the section group. A brief overview is the chapter name, and the groups is the first section name. Okay, we're not starting a new section. Okay, here 1 is fixed, 2 gets here, 3 gets here. Let's draw the table. This is phi 1. 1 stays put. 2 and 3 swaps location. Right, so that's phi 1. So how do we compose those two? I guess that's the question, right? How do we compose? What's the order of composition? Well, the order of composition is we do a rotation, row 2 first, and then reflect. Let's just do the calculation on the side. So this is a new function. You first rotate, and then reflect. Okay? When we write function composition, the operation that gets done first is written on the right. So we write the function composition from right to left. This is like how the Chinese write things in ancient time. Do you guys know that? Chinese people, old Chinese scripts goes from top to bottom and from right to left. And even today, some books in Taiwan are published this way. But in mainland China, we do the usual typesetting, like in most countries, like following the Western world. But in Taiwan, many publications, not all, okay, but still many publications use the traditional way, from right to left, which is kind of cool. And you know what's interesting? In linear algebra, we have row operations, right? And the Chinese has actually discovered what is equivalent to the Gaussian elimination in ancient time. And we call it the column operation because equations are written downward. So the equations are vertical. So the Chinese call them the column operations. Anyway, so the bottom line is when we write function compositions, we start from the right to left. So 1 gets sent to 3 by row 2, and 3 gets sent to 2 by phi 1. So here, this is 2. 2 gets sent to 1 by row 2, and 1 gets sent to 1 by phi 1. So this is 1 here. 1 here, okay? And the last one, 3. 3 gets sent to 2 by row 2, and 2 gets sent to 3. Okay. Does this make sense? Because this turns out to be equivalent to phi 3, no? This is completely equivalent to phi 3. It fixes 3 and swaps 1, 2. Let's draw the picture to verify this result, okay? So let's first rotate by 100, sorry, not 100, but 240 degrees. Okay, so the original triangle after applying row 2 becomes this. And then and phi 1 is this operation. So we fix, so we fix 2. No? Hang on, what's going on? Oh, no. We should fix the new one. We should fix the new one. If we do this, if we reflect this way, this will be fixing 2. Okay, so yeah, we first rotate using row 2, okay, and then fix 1. That's the reflection. No, this is nonsense. Hang on, I'm totally lost here. If you rotate row 2, we get this. And what's the operation of phi 1? Phi 1, look at the table. Phi 1 fixes 1 and flips 2 and 3. Yeah, following that, it should become 1, 3, 2, like so. No? So 3 should stay put, but it doesn't. What the hell? Okay, following this table, have I made any mistake? 1 to 3 and 3 to 2. 2 to 1 and 1 to 1. 3 to 2 and 2 to 3. Yeah, so the table is logical. But look at the picture. 1, 2, 3 rotate. If we rotate 1, 2, 3 using row 2, it looks like this. If we apply phi 1 to be this way, okay, if we apply phi 1, and it becomes 2, 3, 1 this way, huh? Yeah, so 3 stays put and 1, 2 swap. Yeah, so the axis is still here, following this image. So this output right here corresponds to the table. Here, 3 stays put, 3 doesn't change, and 1, 2 gets swapped. So that's the algebra and the geometry. Okay, so yeah, let's compare our answer to the text. The composition, this is a composite map. Phi 1 composited with row 2. 1 gets mapped to 2, indeed. 2 gets mapped to 1, indeed, and 3 stays put. But this is precisely if we simply apply phi 3. Right? The composition is closed. That's the point here. The composition in the symmetry group, I mean, I'm using the symmetry group term already, but in the symmetry of the triangle gives you a new symmetry. A quick calculation shows that row 0 serves as a neutral element. Yes, indeed. And given any symmetry alpha, any symmetry alpha in the set, there exists a second symmetry that undoes the operation phi. This also makes sense, right? For the reflection, the inverse symmetry is simply itself, right? If you reflect, say twice, you get the original back, right? And to undo row 1, what do? Row 1 is rotation by 120. So to undo row 1, we apply row 2. To undo row 2, we apply row 1. Row 1 and row 2 are inverses of each other. And phi 1, phi 2, phi 2, phi 1, phi 2, phi 3, their inverses are simply themselves. So that's indeed, for every symmetry there exists a second symmetry that undoes its own operation. Right. So in terms of its behavior, using the composition as a binary operation, symmetry of the triangle behaves more like Z plus, right? It behaves more like Z plus because in Z plus, as we said, it has a neutral element and it has the inverse for each element, right? So I concur, and that is confusing. Right. So whatever we do, we follow the original image. I guess Rico, I think you're talking about the confusing part of the images, right? Right. So I guess when you apply those operations, you follow the original images. Right. So this is rotation by row 2. And phi 1 is reflection about this axis here. And this way, we don't end up with contradictions. Right. Perhaps the more mechanical way, like the table method, is better. This saves you the confusion. All right, so yeah, this is a very interesting example because it's purely geometric, right? And it has certain characteristics that numbers behave. It has a neutral element and it has a inverse element for each element. So let's put that down. Right. So observe that. Observe that the symmetry is closed under composition. Okay, under the composition operation. And it has a neutral element. A neutral element, say, not say, but the neutral element is row 0. That's a unique neutral element. For each phi, in the symmetry set, all right, it has a inverse, has a unique inverse. I mean, we use alpha. For each symmetry, alpha, there exists a second symmetry. Symmetry beta, such that beta composite with alpha equals the identity element, which equals alpha composite beta. And in particular, let's denote the inverse, right? I think we can do that. Denote beta to be alpha inverse. To be alpha inverse. And we have the list of inverses. The inverse of row 0 is simply row itself. These aren't difficult to find out, but The point is when we read our own notes later, things become much easier to be recalled. Okay, so that's the first inverse, and then the inverse of row 1 is row 2. It undoes the operation of row 1. Row 2 has an inverse of row 1. Okay, so these are rotations and their inverses. The reflections are simple. So phi 1, let me just write phi I. Phi I inverse is simply phi I. And this is true for all I. Okay, so that's it. Yeah. Okay, cool. Each of the sets we have defined in example 1.3 and 1.4 are interesting in its own right. But now we have discovered that except for the example of the natural numbers, they all share a few properties in common. It is this kind of analysis that leads mathematicians to make definitions such as the following. Nice. We're getting into definitions now. 1.6 definition. A non-empty set G equipped with a binary operation. By the way, this is one dot. This means multiplication, and this is a function. Remember, binary operation is a function, and this is a column. Okay, and G times G, that's an ordered pair to G. Right? This binary operation is said to be a group if the following conditions hold. You need associativity. Okay, we need associativity, and we need existence of neutral element, and we need existence of inverses. Right? We need the existence of inverse. The group is said to be abelian. Abelian, of course, this is to honor the Norwegian mathematician Abel. There's a prize named after him, I believe, Abel. And for some weird reason, we're using little a instead of big A. Right? When we write Gaussian distribution, we use big G. Right? When we write Gaussian distribution, we use big G. Or Fisher information in statistics, big F. But for some reason, algebraists use little a. Or Euclidean. And everything that starts with the human name always capitalized, no? But I don't know why. Anyway, that's fine. A group G is said to be abelian if it is commutative. It also satisfies the commutative law. It is customary to use plus to denote binary operations for abelian groups instead of dot. So the box standard group does not have associativity. Abelian groups do. So this might seem like a rather arbitrary choice, right? So this set of what's that? So this set of axioms for groups has three properties. One, associativity. Second is existence of neutral element, identity element, and existence of inverse. Why isn't commutativity included as part of the box standard definition? Why isn't? Is it because associativity is more fundamental? Let's think about that. Right? When we abstract the common properties of all these examples, it's always interesting to bear in mind why certain properties are excluded. Right? Let's think about the triangle example. Let's think about the triangle example here. Is the symmetry of triangles commutative? Let's find out, right? Okay, so we just calculated the composition of phi 1 and rho 2. So let's do the reverse order. Rho 2 composite with phi 1 and see what that looks like. Okay, 1, 2, and 3, let's go. use phi 1 first. 1 gets sent to 1. And then apply row 2. 1 gets sent to 3, so it's 3 here. Already you can see they're not the same. Phi 1 composite row 2 and row 2 composite phi 1 are not the same. So this example right here, the symmetry of triangle does not satisfy commutativity. So that's not a common property. So that's why commutativity is not in the fundamental axiom. Instead, that's like an additional property. Right. So yeah, when we read these axioms, these definitions, it's better not to simply receive them as passive information, because definitions are axioms are rarely chosen randomly. Pretty much never. Okay. There's always some sort of consideration behind them. Why is associativity more fundamental? Well, because in the examples we've seen so far, they all satisfy associativity. They all satisfy, but not always commutative. Right? Even in this simple example of symmetries of triangles, you don't have commutativity. Right? So there's that. Although sometimes commutativity is also important, so we put that as a separate characteristic. So a group, there might be pairs of elements that happen to be commutative, but for abelian or arbitrary pairs will. Yes, exactly. Yeah, for abelian groups or commutative groups, the commutative loss holds for all pairs. Right? And that's a special kind of group. The box standard groups only has associativity, but not commutativity. Right, so that's it. Right. So let's put that down. And do we have that in our example? Yeah. Here it says, although we have not verified the associativity of addition in each of the examples, this can indeed be done. So it follows that these are abelian groups under addition. Z plus, M plus, and C plus. Okay, these are all abelian. Furthermore, the symmetry group is a group under composition, but it's not abelian. The set of natural numbers fails to be a group because it does not contain neutral element. Okay, so we discovered that ourselves. Okay, so the idea is the group axioms. I mean, of course, this needs to be memorized, but based on our understanding. Okay, we don't want to mechanically memorize as this is words written by God Himself. No, these are human creations. These are attempts of economization, because mathematicians they want to solve as many problems as possible in the lowest amount of effort. Everybody loves that, right? So we create these tools to facilitate thinking, and that's it. The definition of group is an example of such attempt. Right? So let's put the definition down. So now we define the group. Okay, hopefully by the end of the stream we can define a ring. That'll be great. Okay, so this definition is now, I think, rather motivated. It doesn't feel like out of the sky. Okay, so that's cool. 1.6 definition. A non-empty set G equipped with a binary operation okay. This looks rather awkward, but anyway, let's just stick to that. G times G to G, all right, is said to be a group if the following conditions hold. A, the operation is associative. All right, is associative. That is, you have for all G, H, and K in big G, we have G times H. This is just an abstract operation. We don't care how you actually would multiply G and H and whatnot. Right? Only the rule matters. The detailed implementation doesn't. Right? We just insist that the dot behaves this way. All right. So that's the associativity, part B, existence of the neutral element. Okay, there exists little e in big G called a neutral element or an identity element for big G, such that by the way, going off topic, do you guys know if there's any other YouTuber that does this sort of thing? I'm not like trying to like brag or something, like just trying to, I mean, if you guys know if like other people do this sort of live study sessions or something like that, do you guys ever know such people exist? It will be interesting for me to check out their content and see like how they approach, right? Because Vizzy has been asking me, is this the way? Okay, is this the way to study math? I mean, I think this is the way, and I can be pretty opinionated, right? That it would, if there's like similar content out there, like for example, I'm an algebraist, try to study, say, probability for the first time, probability and stats for the first time. I think that would be an interesting observation too, right? So anyway, just a thought. So here we have the identity element for such that, yeah, this is true for all little g in big G. God always keeps the good theorems for himself, always. Anyway, so here we have the neutral element axiom. And C, what else? C says, given little g in big G, there exists an inverse. Okay, given little g in big G, there exists an element little h in big G, such that G times H equals E equals H times G. Okay, existence of an inverse where G is where E is the neutral element of G defined above. The element H is referred to as an inverse. It says as an inverse. It didn't say the inverse, no? But I think we can prove the inverse is unique of G. All right. Inverse neutral element or identity element. Okay. Associativity. All right, so the group G is said to be abelian if it is also associative. For all G and H in big G. It is customary to use plus we use plus to denote the binary operation for abelian groups. None that I know of, but I know a few people who do video stream like that, integration competition. Yeah, I know. Like, those are like more like competitive math, right? It's like watching a sport. Like here, this is, I mean, I'm doing it as a newbie, right? I'm learning the stuff for the first time, right? And the point is exactly that, to show how learning for the first time looks like. Because I got so many questions about how do you study X, right? And the answers tends to be pretty generic. Oh, you do X, Y, and Z. And here's this is how it's done. Just unfiltered process. Right, so here G is said to be abelian or commutative. Let's put that down. Because I also seen terminologies as commutative groups or commutative, which is self-explanatory. And yeah, I'm not trying to take shot at other people. Okay, that's definitely not my point. But it's a simple fact that nobody knows all the math. Not even Terrace Tao. Nobody knows all the math. And sometimes you see video titles like all the math for what, right? I mean, the simple reality is there's no such thing, right? Nobody knows all the math, and you don't have to know all the math. Right? That's a liberating part. But the good thing is we can all learn. So, yeah, the point of this stream is to show I don't know all the math, but I can learn, and so can you, and so can everyone else by extension. Right? So that's the idea. The group G is said to be abelian or commutative if this is the case. So why don't we just go back to all the examples we've seen so far and check whether things are group? Right? This is a group. As it turns out, this is a group now. Yeah, this is a group. Let's check 1, 2, 3. Even math knows there are things in math are unknowable and prove exactly. The answer to the question will be very careful and without leaving things to luck. Yeah, so I mean, the answers of how to learn X tends to be pretty generic, and I think that frustrates the people who ask the question, right? It feels like, oh, I'm not really getting a real answer, and here's I'm giving the answer. I mean, I just answer the question by doing it, because I've got these questions too, like how do you read books, how do you read papers, how do you study probability, and to gain some sort of understanding. I mean, the simple answer is there's no trick to it, right? But that's the process, right? So, all right. So let's revisit these examples. Is this a group? Z plus, is this a group? Of course it is. Addition is associative. I mean, I'm not proving that. Okay, I'm not proving that. We just take our knowledge from the kindergarten as granted. Okay, so addition is associative because in order to prove this, you need an axiomatic definition for Z. Right? You need to go back to Peano axiom and define what it means to add. Right now, we're just using our knowledge from kindergarten of how we manipulate addition since kindergarten, right? So this is indeed associative. Addition for integers is indeed associative, and the neutral element is 0. And for every integer, there is an inverse, additive inverse. So it is a group. And it is also abelian because addition is also commutative. Yeah, so we're going over them one by one. Is a group. And is abelian. All right? B is not a group. Nice. C is a group and is abelian. Okay, D is a group and is abelian. Okay, Q star dot is a group and is abelian. Q plus is a group and is abelian. Okay, everything here is our except B is a abelian group. Okay, and the interesting thing about the symmetry, actually, you know what? Let's put a separation mark here. To make things easier to read. In the light of the definition, the symmetry triangle, symmetry group of triangle, this is a group but not abelian. This is a group but not abelian. Okay, awesome. Awesome. Okay. Anyway, so here we have the definition, our first big definition today, which is really exciting. Vizzy, if you're still here, let's do one of the problems, shall we? By the way, let's read the remarks and 1.8. We'll get to the exercise. Since a group consists of the non-empty set G along with the binary operation, we normally write G. This is like the ordered pair notation, right? G and the dot to denote a group. Informally, when the binary operation is understood, there is no risk of confusion. We may refer to a group G and drop the dot from the notation. And we write GH to denote G dot H. Okay, so understood. There's no need to put that in the notes. I don't think this will confuse anyone. GH. This simply means G dot H. Okay? We shall leave it as an exercise for the reader to show that if G is a group, then it admits exactly one identity element E. Okay, the uniqueness of E. This needs to be proved. And given that G is in big G, the element H satisfy the property of the inverse is also uniquely defined. For this reason, we speak of the identity, Z identity. Okay, we speak of Z identity elements of the group G as well as Z inverse of G. We should also adopt the notation G inverse to denote the unique inverse of G. All right, awesome. So none of this should be surprising, but it should be proved. It should be proved, which is one of the exercises. Two exercises, in fact. Example. Although we have not verified the associativity of addition in each of the examples from 1.3, this can indeed be done, and so it follows that these are abelian groups under addition. These are all our abelian groups under addition. Furthermore, actually, you know what? Let's put this down. We verified that, right? We just verified on our scrap paper, on the side, that the symmetry of the triangle is not abelian. Right, let's put that down, because we also verified that ourselves. So put it here. It's not abelian since. Okay, row 2. No, composition. Phi 1 equals Phi 2 and now equals Phi 3 equals Phi 1 composition with row 2. All right, it's not abelian. Capitalize that. That's our first example of a non-abelian group. Certainly worth noting. Okay. Anyway, let's get to the exercise. Okay, exercise 1.1. Prove the uniqueness of the identity element. Exercise 1.2, prove the uniqueness of the inverse. I believe these are classic exercises. Usually the first one in a group theory class. Okay, exercise 1.1. Okay, let's just paraphrase the question. Prove that the identity element of a group is unique. Okay, and we'll use the setup here. Suppose that E and F are both identities, right? So this is what we may you take a peek at exercise 1.5, scratching my head. Okay, 1.5 says what? 1.5 says denotes that the isosceles triangle which is not equilateral. Determine this. Okay, sure. We'll come to that. Okay, we'll come. I think we can do pretty much exercise 1 to 1.1 to 1.5. No, we have all the definitions we need, right? Okay, so we'll come to that. And also 1.6, huh? 1.6, can we do that? It introduces all the context. All right. Wow, I think we can do everything. I think we can do all the exercises. We have all the machineries we need. Unless there is something about subgroups and stuff, which we have not yet covered. Because these are additional examples, which is cool. We'll come to that. I mean, when we solve exercise, we'll come to those examples. Nice. But first things first. So prove the identity element of the group is unique. Proof. Okay, let's use the setup. Suppose E and F in G are identity elements of G. Okay? Then, by definition, for all little g in big G, we should have EG equals G equals to G, and also GF is G equals FG. All right? So this is the setup. We need to show E equals F. So why don't we take G to be F in the first set? So F, let's write F equals EF. Right? By G equals EG for all G, if we just substitute G equals F, we get F equals EF. But then we substitute GF equals G. You just get E, huh? You're done. I know it looks really stupid, but here we're using, let's put a star here. Put a star here and a double star here. Okay, by using star, we substitute G equals F in star, we get F equals EF. And then we substitute G equals E in double star. And we're done. No? Okay, so that's it. That's exercise 1.1. Exercise 1.2. 1.2. So what do we want? We want to prove that for each element, its inverse is unique. Right? Prove that the inverse, I'm sorry, um, the inverse um, of any element, of any given element of a group. Since any given group element is unique. Prove that the inverse of any given group element is unique. Right. So yeah. Proof. So let's give ourselves an arbitrary group element. So suppose G is in big G. Suppose G is in big G, and now what? It must have, by the axiom, it must have an inverse, A inverse, okay? So by definition of groups, G has an inverse, say H. And this means GH equals E equals HG, where E is the identity element, or yeah, or the neutral element of G. All right? So we have that. It has n inverse. It has n inverse. And now let's say you have another inverse. And now you have another inverse, say H1, H2. Let's suppose H1 and H2 are inverses of H. Need to show H1 equals H2. Right, so this is what we want to do. How do we go about showing that? How do we go about showing that the inverse is unique? Can we express the inverse? Say H1 equals something. Can we do that? Here we have G of H2 equals G of H1 equals E, and H1 of G equals H2 of G. So you want to do some sort of cancellation law, right? You want to cancel out G here. But how do you justify that? I suppose you can write it this way. You can, if you want to cancel out G, you can left multiply that by H1. So let's write it this way, okay? H1, let's write it as EH1. This is certainly true. And we can write E as in one of the forms which we desire. Actually, you know what? Let's do it this way. This is H1 times E. And write E as GH2. And now H1 times G, this one is E. I'm using associativity. Let's do it slowly. This is H1 times G. I'm using associativity. H1 times G is E, EH2, and therefore just H2. And we're done. And that's the end of the proof. All right? Because the idea is to look at, okay, you have GH2 equals GH1. You want to cancel out the H. You can want to cancel out the G. How do you cancel out the G? Well, you can multiply, left multiply by H1. This way G gets canceled. That's the end of the proof. So hopefully these aren't too difficult, okay? And yeah, and now let's look at 1.3. Exercise 1.3. Let G be a group. Suppose that you had, suppose you have G squared equals E for all G. Then G is abelian. I mean, before doing the proof, I mean, what does this remind us of? G squared equals everything jives so far, yeah. So what does this remind us of, right? G squared equals E. So that means G is its own inverse. It kind of is like the reflection thing, right? When we're doing reflection, the three phi's, remember, was a triangle. Phi 1, phi 2, phi 3. They all satisfy phi squared equals E, or rho 0 in the triangle case. What this exercise says that if we just look at the reflection, first of all, the reflections themselves form a subgroup. We haven't touched subgroup, but I think this is self-explanatory. It is a subset of the original group, and itself is a group. Right? That's called a subgroup. So the subgroup of reflections is abelian because they satisfy this property, G squared equals E. Is that the case? Is that the case? I mean, it certainly feels that way, right? If you, let's say, if you reflect, where's the picture? Yeah, let's look at the picture. For example, let's say if you reflect here, if you reflect about this axis, you fix 1, right? Fix that. You get this result, phi 1. And then we reflect so that 3 is fixed. I'm talking about reflecting with respect to this line here. What do you get? You get 3, 1, 2 this way. Okay, so this is phi 3. But what if we reflect phi 3? Reflect using phi 3 first. If we reflect phi 3 and we get 2, 1, 3 this way, and then reflect with respect to, reflect with respect to this line, and you get 2, 3, 1. Oh, they're not the same, huh? Hang on, am I stupid? No, let's redo that. Let's redo that. So this is phi 1, you get 1, 2, 3. Reflect with respect to phi 3. Yeah, this is correct. Phi 3, what do you get? 2, 1, 3, that's phi 3, and then phi 1. What's phi 1? Phi 1 is fixing the top. 2, 1, 3, huh? Still not abelian. Oh, actually, never mind. I was stupid because the reflections don't actually form a subgroup. No. So reflection don't form a subgroup because reflection does not have a neutral element. Reflections don't have a neutral element. No. So yeah, Wrigglestat, just undo everything I just said. Okay. The reflection subgroups of a non-abelian group can be abelian. I mean, that's true. That's true. But what I just said was not an example. I think what you typed is true, but I don't think we found a good example. Yeah. Yeah. All right. Okay. So what do we have here in the exercise? I couldn't quite find a good example for that exercise, but that's okay. We can just do the exercise for their own sake, and we will keep in mind and to see if there's any actual concrete examples. So far we're doing okay, right? So far we're doing okay. Let G be a group. Let G be a group. Suppose G squared equals E for all G in big G. Nuke from the neurons. Indeed. In big G, prove that G is abelian. All right? So that's the exercise here. Prove. Okay, so how do we approach this? To prove that G is abelian, we need to use the definition. So suppose let G and H be in big G. Okay, need to show GH equals HG. That's our goal here. I mean, inspired by exercise 1, we should cook up an E in the equation, right? It's like multiply by 1. It's a common trick in algebra. Yeah, I guess when we had last night's stream, somebody commented, I think someone named Sir EJ, said the most difficult mathematics, most difficult trick in math is to somehow randomly plus a 0 and the times 1, which I totally agree. Right? Anyway, so, but I guess based on the previous exercise, this should not surprise us too much. Right, so here, let's try GH equals, I don't know if I should left multiply E or right multiply E. I have no idea. But let's just try. Let's try left multiply EGH. This is certainly true. And what do we want? We want HG, right? We want HG, so we want HG. How do we cook that up? If let's just say, can I maybe put E equals H squared? Let's HHGH, does that work? No, it doesn't, huh? I want HG at the end. HG at the end. Okay, so this isn't quite useful, but let's not erase that. We might come back to that, but let's just try right multiply E. Okay. We want HG. We want HG. So let's say if we write GH GG, does that work? How do we cook up HG then? Pull a 1 out of the thin air. Yeah, exactly. Yeah, the ChatGPT stuff last night smelled a lot like that, yeah. Basically, how do we want our goal to be HG. Let's start from GH. Right multiply E. What about HH? Well, HH is E, and the middle HH is E again. That's not terribly helpful. You get GH equals to GH. That's not very helpful. So perhaps let's sandwich the, the GH in the middle. Does that work? Let's try HH. We want HG, right? GH and GG here. It does not look like we can somehow remove the HG in the middle. I mean, perhaps we can build on exercise 2, right? Because if G squared is E, we can say G is its own inverse. So let's, okay, let's just say, since G squared equals G equals E for all G in big G, we can write G inverse equals G. G is its own inverse for all G. Right? So that's valid. Can we work from there? I mean, we want GH equals HG, but GH and HG should also satisfy the assumption, no? So let's try maybe square this. Let's square GH and see what happens. By definition, this is GH. And this should be E. It should be GH. Is there anything we can do? So, well, um, let's left multiply G on both sides. I'm just performing random steps, okay? You know, so GE is GGH. Is that helpful? Well, this gives us G equals, because left hand side is G, on the right hand side you got a GG, which is E, so the right hand side is just HGH. Because I'm trying to cook up the GH equals HG. We're kind of getting close, right? And then we multiply H on the right. Yeah, and that's it. So that's it. We multiply H on the right. The left is GH, and the right is HG, and then H squared. H squared is E. So we're done. That's it. Because this is unneeded. I'm going to just write since GH is in E, then blah blah blah. Okay, since GH is in G, E is GH squared. So there's that, and then left multiply by G. You end up getting G equals HGH, and then right multiply H, you get the result. All right, that's 1.3. It's a little bit trickier, right? But okay, I think it's still doable. 1.4. 1.4. I concur. This is very different from my usual way of thinking. I am more of an analyst at heart. Real and complex analysis, all of those stuff. We tend to argue with inequalities. And this is pure equality, right? Algebra is all about equality. As my old supervisor often say, algebra is about equality, analysis is about inequality. And quite often in analysis, if you want to prove an equation, you would go something like this. You prove the left-hand side is greater or equal to the right-hand side, and the right-hand side is greater or equal to the left-hand side. So the two things must be equal. This line of thinking pretty much never happens in algebra, as far as I'm concerned. Right? As far as, in my limited experience with algebra is concerned, right? Because not all the structures in algebra has this order relation. But in analysis, if you talk about convergence, you always deal with inequalities, right? In analysis, you want to prove a property of the integral, and bound and squeeze it, exactly, right? This line of thinking rarely happens in algebra. Instead, you're just manipulating these rules, and there are so many options, and it feels kind of random. And I just got lucky, to be honest, because I was just thinking, okay, how can I cook up a HG and H and GH on each side, right? And I could have taken a lot longer. I think I just got lucky. Anyway, so let's keep going. 1.4. In example 1.4, we determine that the symmetry group of the triangle, right, is a non-abelian group with 6 elements. And we determine all its elements by observing what each symmetry does to the vertices of the triangles. Yeah, to determine the symmetry of the square, the symmetry groups of square. In particular, how many elements must it have? Okay, so let's first do a little combinatorics exercise, like how we did for the triangle. Right, so exercise 1.4. So this is about part A. Actually, find part A. Find, determine the set, the symmetry of the square. Okay, how do we do the symmetry of the square? Do we even have a square in Microsoft Word? or just this QED symbol. I want something that is not solid, you know. Perhaps we can insert a symbol here. Yeah, there is such thing. Nice. But I don't know the code for typing it, so it's kind of annoying every time you have to. Oh, what's going on? I want the square, no? Give me the square. Okay, nice. The square with the composition. Determine this group. The group of symmetries of a square. In particular, how many elements must it have? Question mark. And part B, is it abelian? Okay. Interesting. So first let's figure out how many elements must it have. Hang on, what's going on? I wanted a square, no? I wanted a square in the middle. Would you give me that? More symbols. The square thing. No? Yeah, that'll be nice. Okay. Is it abelian? I mean, first let's decide how many elements must it have. Well, let's draw a picture. So here's a square. No need to draw a big square. So this is 1, 2, 3, 4. All right. Well, obviously 1 has 4 ways to go. And after that, 2 has 3 ways to go. 3 has 2 ways to go, and 4 has no option left. So that's 24. Nah, the backslash square doesn't work. Okay. Guess what riddle? Wriggle. We'll finish exercise 1.5 and call it a day. Because I got stuff to do later. Okay. Is that okay? Yeah. Well, I mean, we didn't quite have the chance to get into rings. That's fine. We'll continue this another time. All right, so, well, we have 24 elements, huh? So this grows rather quickly. I think this is the same as the permutation group, no? I think this is the same with the permutation group, huh? So anyway, let's think about rotations. Okay, rotations by 90 degrees. So let's denote rho I, rotation, clockwise rotation, about the center. By 90 I degrees. Okay? And I equals 0, 1, 2, 3. Right? If you get 4, then you rotate it by 360, then it's the same as I equals 0. No, I'm not. I'm not given my time. It's like I'm learning stuff myself, right? It's kind of also for myself, right? So anyway, so here we have But yeah, thank you. So let's say, let's draw these results. So row 0, I just want to relabel the picture. One gets here, two gets here, three gets here, four gets there. Oops. Okay, so that's row 0. Oh, no, the row 0 is simply do nothing. What am I talking about? Man, I really should perhaps take a break, huh? So, yeah, this is row 0. And so, yeah, I'm not going to draw the original picture every time. This just means the original picture after applying row 0 becomes this. All right, so this is row 1. And row 2. Row 2. And I think at some point we will talk about the generator of a group. At some point we'll get to that. Hopefully not too long. But I don't know. Like this note is supposed to be about rings and fields, right? Group is just like a preliminary definition. We're not going to go in depth about groups. Okay, this is, and then row 3. One gets here. One gets here. Two gets here. Three gets here, and four is here. So that's all the rotations, no? This should be all the rotations. And also we got symmetries that do what? Sorry, no, not symmetries, but the reflections. Well, you can reflect about horizontal and vertical axes, I suppose, as well as what? As well as, well, you can reflect about the diagonals. That also works. So how do we denote that? What would be a intuitive way to denote such reflections? I mean, you can say reflect left, right, or reflect up, down. Perhaps that's I don't know, like, because right now you're fixing two elements, no? Hang on, did I? Yeah, I think I removed the original picture. Yeah, this is the original picture. Let's just say reflect phi. Let's use phi for reflection, following the note. For triangle, phi up, down, UD. How about that? Phi UD. Reflect up, down. And you get something like this. And we can reflect left, right And diagonals, yeah, exactly. Reflect left, right. And let's call that phi L R, reflect left, right. And let's reflect the diagonals. Let's say this 1, 3 diagonal, sorry, this 2, 4 diagonal in the original. How do we describe that? This is like the northeast, southeast diagonal. How do we describe that? But anyway, it fixes 2, 4, right? So let's just write phi 2, 4, following the triangle symmetry notation. Sometimes coming up with good notation is half of the work. Like think about dx, dy. This is genius notation. All right. So this is the reflection that fixes 2, 4. All right. You also have the reflection that fixes 1, 3. And by the way, I'm going to draw the axes of reflection to make them obvious. So this is phi 1, 3. This is phi 2, 4. This is up, down. And this is left, right. Okay, so these are only 8. We got 24. I guess the rest are compositions. Huh? I mean, yeah, the rest should be compositions, huh? But an economic way to display those would be like a table, right? So let me just draw a big table. Well, actually, you know what? Let's type that. Let's type that. Okay, so imagine having 24 rows in the table. Is it better to use matrix or table? Let's use table, huh? Number of columns, number of rows 25. Number of rows 5. That's okay. All right, so you got 1, 2, 3, 4. You just want to do all the permutations, right? Enumerate those. Is there an efficient way to do that? I'm not super well versed in combinatorics. Perhaps there's a way to do that that's efficient and not confusing. Well, first let's just do the identity. That's trivial. Let's call that E. Right? And let's say if we fix 1, 2 and change 4 and 3. Okay? And then we fix 1 and we allow the rest of the 3 to permutate. So we have 2, I already exhausted. So we have 3, let's say 3, 4, 2. 1, 3, 2, 4, 1, 4, 3, 2, 1, 4, 2, 3. Right, so these are 6 rows. That's 3 times 2 times 1, or 3 factorial. And I think the rest can be easily reproduced if you just change the first 6 letters, okay, to be 6 2, 6 3s, and 6 4s, like this way. And then you permutate the rest of the 3. Right, like this. In the triangle example, the composition is one extra isometries because the composition is always the original. Yeah, the original, yes, that's true. Because in the triangle example, by combinatorics, you should have 6 isometries. You should have 6 symmetries. And you just enumerated 6, so you're done. Right? But here, things are a bit more complicated. So, yeah. So bookkeeping becomes more painful. 1, 3, 4, I suppose. Yeah, 1, 4, 3. It's really mechanical and not the most exciting thing in the world, but let's just get it over with. It's not that hard. All right, 3. You got 1, 2, 4, right? So 1, 2, 4. Keep 1 fixed. 1, 4, 2. 2, 1, 4. 2, 4, 1. 4, 1, 2. 4, 2, 1. Actually, is that possible? Is that possible? Because the order has to, because you have to be like 1, 2, 3, 4 this way, right? The order has to, you know what I'm trying to say? If you traverse along the perimeter, the order has to be in a certain way. These pictures we've drawn obviously satisfy that property. But let's just say if any of those permutations, because let's just draw an obviously false picture. How many symmetries are in the square? Can we say we have 1, 3, 2, 4? This is not possible. Because 1 and 3 is not adjacent, are not adjacent. This is not an okay picture. Are you with me? Yeah, this is, let's say, I mean, here you can just say from a permutation perspective, you're gonna fix 1, 4, and then exchange 2, 3, but that's not okay. It's like you're twisting the paper. The set of those vertices are unordered. Yeah, but they have to correspond to the geometry, right? My point is 1, 2. If you just write it as a set, yeah, it's not ordered. It's not ordered. But think about the shape. This is not valid. 1, 3 are not adjacent. It has to respect the original shape, no? 1, 3 are not adjacent. So we're really talking about is a graph. It's not just a set of vertices, it's a graph. I'm using the language of the graph. A graph is a set of vertices and a bunch of edges. In the original picture, there's no edge between 1, 3, and 2, 4. You got to keep those edges as well. There are 4 edges in the original. I mean, there are 4 there are 4 vertices, right? There are 4 vertices. So if you connect all the vertices, you should get 6 edges, combinatorics, or straight from the picture, the diagonals and the sides, right? But the square only has 4 edges. We cannot get something like this. This is not valid. 1, 3, 2, 4 on this picture is not valid. Yeah, I guess we were dealing with triangles that went under my radar. It becomes really obvious when we're dealing with, because I figured there shouldn't be that many symmetries, no? The edges 1, 3, and 2, 4 don't exist. Which makes things a little bit trickier. But let's think about, let's say we have 8 geometric transformations that were listed here. Let's try, let's say, composing some of them. Can we get new things? Can we get, let's say if we compose, if we compose rotation, you still get a rotation. So there's nothing to say about that. If we compose, let's say, 2 reflections, and what we get? If we compose 2 reflections, what do we get? If we compose, say, phi UD and phi LR, what do we get? Well, you flip it up, down, and then you flip it left, right. So 4 gets here, 1 gets here, 2 gets here, 3 gets here. Four gets here, 1 gets here. So that becomes row 2. You with me? So if we first do up-down reflection and then left-right reflection, what we end up getting is 4, 1 are on the right edge and 3, 2 are on the left edge, which is exactly row 2. So that's not a new composition. And you can never get something like this, 1, 3, 2, 4. So the thing is there even other transformations or even other symmetries are possible? I mean, these eight are obviously are. Are there anything else? Because when we did this reasoning, right? When we did this reasoning, we said 1 has 4 places to go, obviously. But after 1 is fixed, 2 only has 2 places to go, not 3. Think about it. If, let's say, 1 is fixed, then because 2 has to be adjacent to 1, it does not have 3 possibilities. So this calculation is naive. This doesn't work. Instead, it should be 4, because that's all the places where 1 can go. But after 1 is fixed, 2 only has 2 places to go, because 2 has to stay adjacent to 1. So think about this. So if you have an edge with 1, 2 now fixed, and 3 has to be here. 3 has no other options. 3 cannot be here. And 4 has to be here. So that's it. It should be 8, not 24. Right? But anyway, that's okay. I mean, we can, that's the reasoning, right? That's the reasoning. If you fix 1, 2 only has 2 places to go. And after that, 3 has only 1 place to go, and 4 is determined too. So you don't need this giant table of 24 rows. Because I was getting sus. And yeah, that's it. Yeah, we were doing a permutation group, but it's certainly, I mean, the permutation groups is isomorphic to the symmetry of a equilateral triangle, but not for the square. Does it have a name? I think, I mean, I read it somewhere, like, is it called a dihedral group or something like that? Is it dihedral group, right? Is it called a dihedral group? But anyway, it doesn't matter. So, yeah, I think we nailed this. At this point, we nailed this, right? The original 8 transformations are all the possibilities. There's no more. Okay, let's check. Is this abelian? Probably not, huh? Rotations themselves must be rotate. I mean, this is a 2D rotation after all. 2D rotation in general is commutative. So you're not going to find a counterexample among the rotations. So let's work with the reflection. We already calculated one reflection composition. We reflect up down first and left right. Dihedral, yeah, definitely not by properties of R3, no. Yeah, we were getting naive. I was naive, so I did this calculation here. That's wrong. This is correct. Anyway, so I mean, yeah, it's a good lesson. It's a good lesson because when we're doing the triangle, there's no indication that the symmetry group of the triangle is any different from a permutation group. But well, when n equals 4, things are different. Okay. All right. So here, I mean, let's try to do the opposite. Let's first flip the square left right, and we get 1 4 2 1 2 1 4 3 in this manner. And then we flip upside down. Flip upside down. So 3 4 on top, 2 1 at the bottom. What's that? What's 3 4 on top and 1 2 at the bottom? It's not here. What the hell? We're supposed to have enumerated everything, no? What the? Okay, new picture. Something is not right about the notes above. Or is it? So yeah, I was saying that that's the original. This is original. Oops. Hang on. No, that's not what I want. Okay. So apply the up-down transformation first. And then apply the left-right transformation. Okay, and then apply the left-right transformation. What do we get? Well, you get a square for sure. But the letters are now, or the vertices are flipped left, right. So 2 3 goes here. 3 sorry, no 2. I mean 3 2 goes here. 4 1 goes here. what does the final picture look like? 3, 4, 2, 1. 3, 4, 2, 1 is row 2. So therefore, phi UD first, phi LR second is equals row 2. Okay? So now let's reverse the order. Let's do left right first and up down later. Flipping left right gives us this. This is flipping left right. And then we flip up down. The cat wants to play. Oh, can you hear her? So that's 3, 4 on top. And come on. Yeah. But I'm trying to say is what is this equal? I mean, it's supposed to be one of the 8 transformation, no? Come on. Come on, kitty. Soon, okay? We'll finish this up. What is this? What is this transformation? Is it rotation? It's the same. It's the same. It's still. Let me double check. So first left, right, and then up, down. This is the same as this. So that's not a counterexample. So left, right, and up, down do commute. So that's not a valid. Okay, we got to look for something else. So phi LR first, phi UD second is the same as row 2. Yes, flip and flip are okay, rot and rot okay. But okay, so let's look for a combination between rotation and reflection, right? Okay. I mean, I haven't checked all combinations of flipping, so I'm not quite sure. So anyway, but this is not a counterexample. Okay, so why don't we just look at row 1 and flipping up and right. Okay, so let's do that. So let's try to modify this picture and see what we get. Okay, so let's first flip and then row 1. Okay, row 1. First flip up, down, and then row 1. Rotate 90 degrees. So 3 gets sent here. Okay. 3 gets sent here, 2 gets sent here, 1 gets sent here, 4 gets sent here. So phi UD composite with row 1. Let's take a look at the table here. What is this? 1, 4, 2, 3. What's 1, 4, 2? 1, 4, 2, 3 is 5, 1, 3. It fixes 1, 3. Good. This is 5, 1, 3. All right, let's keep going. Now let's flip the order of the operation. Row 1 first, phi ud second. Okay, that's good. Row 1, the outcome of row 1 looks like this. And then apply phi ud. You flip it up and down. So 4-1 gets sent to the bottom and 3-2 on top. What's that? That's phi 4-2. Okay, so that's indeed a counterexample. Okay, so that's a counterexample. Oh, yeah, this is a counterexample. Okay, let's finish writing this up. So this is row 1 first, phi ud second. As we mentioned, this is fixing 2-4, so this is phi 2-4. Therefore, not abelian. All right. Awesome. Confirmed this is not abelian. Okay, so we solved this problem. Okay, so we solved this problem. Yeah, this is completely done. All the members, the symmetry of a square, and not abelian. All right. Let's look at the. Hang on. Where's the notes? Yeah. 1.5. Let gamma denotes an isosceles triangle which is not equilateral. And this should be less symmetric, right, compared to the equilateral triangle. Now I have confidence in this. Gave me more of a flavor what to do. Yeah, let's figure that out. So gamma looks like this, right? So it's a pointy or flat isosceles triangle. It's not equilateral. Okay, so let's say this is 1, 2, 3. I think it's just 2, right? One is the identity, the other one is fixing 1. The reflection that fixes 1. That's it, no? Can you think of any other? The difficult part is always proving that's it, right? There's no more. Yeah, I don't think we can think of. Can we come up with an argument that that's everything? I mean, once again, I guess consider how many points you can go, right? Because 1 can only go to 1, right? That's the image. 1 can only go to 1. So 2 has 2 options, and that's it, right? So it's kind of silly. Right. So basically, the size of the symmetry group tells you how symmetric an object is, right? If you have a circle, you got infinitely many symmetry. So it's a lot more symmetric. So a circle is a lot more symmetric than a square. And a square is more symmetric than a triangle, no? Yeah. Yeah. So that's it. All right. So let's call it a day. Okay. So we managed to understand group, the definition of group. Okay. We didn't have time to get into the subgroups and whatnot, but I think it will be not so difficult to follow the supplementary examples. Okay. That's it for today. I hope we had fun. I certainly did. Abstract algebra, first attempt.
doesn't feel like it's killing me, okay, which is a good thing. Perhaps I mean, of course, something down the road will definitely kill me, but but whatever doesn't kill me makes me stronger, right? No, thank you for joining the stream. Bye now.